Okay, in regards to your lab rat, I'm going to talk about a few things and try to help you with how to finish out your reports. So we did not do reaction number 1, but you've done reaction number 2. To be honors, you have this extension to include 3B with the extension 4, 5, 6, the yeast, the honors, and then 7B, the extension, and we did not do 8. So as far as your report goes, you don't have this one to complete, but you've got 2, 2B, 3, all the extensions on that, 5. Honors, you have a chart that you've got to put in right there that you design yourself. And then we're not doing 8. Okay. So this first page is a lot of new stuff, and so I'm going to step you through some things here. So for reaction number 2, we have copper chloride combining with iron, okay? We don't know what the charge of the iron is, and I'm going to be talking about that soon, that irons have more than one charge, either a +2 or +3, and there are certain properties we look for in order to figure out which one we're working with, okay? So I'm leaving these blank for right now. The main thing is you guys saw red stuff come out the bottom and precipitate. That's our evidence for our copper. That was solid. And our iron went into solution. That's why we got the change from the blue to the clear. Some of y'all got a change from a blue to like a yellow, but you had a change in your color. So here are our reactants, copper 2 chloride and iron. States of matter for the copper 2 chloride, anything that was not water is going to be aqueous because the way I made it. Okay, it's like making Kool-Aid, that's aqueous. And then I have my iron chloride and the copper. This was a single replacement reaction, and I'll show you a little bit more about that in a little bit. 2B was very similar. It was the copper 2 sulfate. That's all we replaced out to see if we had similar reaction. Everything else stays the same. Again, we don't know which iron we have. It's also a single replacement reaction. Okay, again, we're using our evidence. For reaction number 3, you guys took copper chloride and you combined it with ammonium. It was actually ammonium and water. Okay, we produced copper hydroxide on the other side and ammonium chloride. Okay, we're going to be working on this crisscross soon, and how do we make those products on the other side? We're going to work on it soon. This was actually the solid that came out in solution. Okay, and so I end up with copper chloride, and I should have finished that name out right there. This is copper 2 chloride, and it's actually ammonia and water, all right? And I have copper 2 hydroxide and ammonium chloride was produced. That was actually a double replacement reaction. Now, on the extension, when you put the sulfuric acid in there, 3 is actually what we call in chemistry an equilibrium reaction, okay? So you did a reaction and you did what we call Le Chatelier's principle. Okay, all it means is we stress the system does what it has to do to get out of stress. Okay, so as far as this goes, this is a reverse of that, of number 3. So here I have copper 2 hydroxide with ammonium chloride, and my products are copper 2 chloride and ammonium water. Okay. And it's also a double replacement reaction. It's just reverse of it. So similar thing with the copper 2 sulfate and ammonia. Again, we got copper hydroxide. We still got chunky monkeys in there. Very similar. Okay. And as we said earlier, since it's an equilibrium reaction and I swing it one way and I swing it the other way, it's a reverse of 3B when I throw that sulfuric acid in there. Sulfuric acid is just there to what we call pronate the ammonia and reverse that reaction back to what we had. Okay. Then you did the hydrochloric acid with the zinc, okay? You saw bubbles being produced. You guys may have not recognized what it was. If you were lucky enough and you got to pop as you brought the wooden spoon in, that was the hydrogen gas that was popping, okay? And that was a single replacement reaction. Then you had the iron 3 chloride with the sodium phosphate. This is a double replacement reaction, so we're just going to switch our partners. Iron's going to get phosphate, sodium gets a chloride, and I produce iron 3 phosphate and sodium chloride. I I actually have one of those wrong. This one here is actually solid. It's not aqueous. Okay, because you did have a solid, and sodium chloride is dissolvable in water, so it has to be the iron 2 phosphate. That's actually a solid. The yeast one, this one was not meant to throw you off, but you had to think about it. So you had the hydrogen peroxide, and when you put this splint in there, you noticed that it glowed. A lot of you commented that the only gas you knew that would make it glow like that or reignite was oxygen. You were correct. The yeast was a catalyst, so my hydrogen peroxide was undergoing decomposition and producing water and oxygen. So when I do the sugar with the water, again, the yeast is a catalyst, okay? And when you put your splint in there, you didn't really get anything. It went out, right? Well, there was carbon dioxide that was being produced in that reaction. This is actually a redox reaction, or exchange of the electrons, okay? And the other thing that was produced was ethanol, which was important. At one time, we were looking at producing that for alternative fuels. Okay. And then honors, you'll have to figure out your extension there, depending on what you did. So then we did an acid-base reaction. We did 2 of those. We took, first of all, sulfuric acid with sodium hydroxide, and we produced sodium sulfate and water. And then hydrochloric acid with sodium hydroxide produced sodium chloride and water. So very similar reactions. They are an acid-base reaction, and all we were doing, we were using an indicator to swing it one way or the other way. And one thing most of y'all started picking up on was the amount that you were having to put of their sodium hydroxide, and that has to do with the fact that your sulfuric acid that you were working off of was a 1 molar, and your sodium hydroxide was only 0.1. So a lot of y'all noticed a difference, and I'm proud of you for noticing that. Okay, difference between cations and anions. Cations are always going to be our positive charge ions, and our anions are our negative ions, okay? So this is always going to be who's written in the front. This is always who's in the back. But this has to be ionic bonds, okay? So it cannot be covalent or polar covalent. So it can't be the water. It can't be CO2. It can't be O2. Those don't work, okay? But we're talking about like sodium chloride, and I'm only going to do one. Sodium is a +1, calcium is -1. So this is my cation because it's positive, and this is my anion. Okay, so give examples. Polyatomics, give 2 from your lab. This is a new vocab word for you guys. So polyatomics were these endings that you didn't really recognize, okay? So there were some nitrates, there were some sulfates, hydroxide. There were plenty of them to work with. There was even a phosphate that we worked with in our lab, okay? So polyatomics are just units that act as one, okay? Law of conservation, this is oldie but a goodie, so I expect you should know what law of conservation means. 3 subatomic particles and who discovered them and their charges. This is a review of stuff we've already done. What are valence electrons? How many does sodium have? Those should be gimme points to you, okay? I also gave you in your folder this document as well. I love this document because it's got the charges on there. And please note that you've got some of these in here that've got multiple charges, and that's what's we're gonna talk about. What does it mean and how do we figure out what they are, you know? Some old ones, but good ones. What group does chlorine belong to and how many valence electrons it has? So surely you've got your periodic table marked up. You've got that ready to go, and you can do that. Difference between liquid and aqueous. Liquid has to be 100% that. So water is a liquid, okay? Make sure you write in complete sentences. I'm doing this real quick. Aqueous means that I dissolve something. So a lot of times what I'm doing behind the scenes is I'm putting a solid in there, okay? I measure out maybe, let's just call it CuCl2. And then what I do is I go in there and I fill water to the line, okay? And I say, voila, I have 1 molar of CuCl2 because of my ratio between a copper chloride and the water, right? That's aqueous. It's like Kool-Aid, okay? The way you used to make Kool-Aid, you dump it in there and you add water to it, all right? Characteristic ionic bonds. That's from your old lab, guys. You should know. We've worked on ionic bonds. We did some different stuff with it. Covalent bonds, again, that's another one. Equilibrium, honors, I mentioned that in this video, okay? You have some examples of it. Post-slam, standard 5 like always. I'm going to do a little bit more on this as well. Make sure you're writing complete sentences, and I can promise you, you all have errors, okay? So, periodic table, I've included my periodic table in here for you. Also, there's a review over your Lewis structures, as always, trying to keep that fresh on your mind. Okay, again, difference between pure substances, elements, and compounds, as well as ionic bonds and covalent bonds and their properties. And then this is the new slides that I put in there for your types of reactions. And so I was giving you names of types of reactions, and this is what they are. We have 5 general ones we use in the state of Texas. We have combination synthesis, decomposition, single replacement, double replacement, and combustion reactions. I tried to show you each one of those, okay? Your Bunsen burner is your best combustion reaction. Also, there's some solubility rules, because that's one of the things we look at, is we have to figure out who's dissolved and who's not, okay? And then this is just showing how to write out reactions, okay? All right, and live long and prosper.